you know, we are from Potenza. Actually, our lab is located in Tito Scalo, in the south of Italy. Although we are in the south of Italy, we have snow, and actually, even though we have so much snow, sometimes we can get release because of the need of finding solution to problems. This is something that is related to laser as well. So we know that Taunis Basov Prokhorov got the Nobel Prize in Physics in 1964 for fundamental work in field and quantum electronics, thanks to the construction of oscillators amplifier based on Maser laser principle. But actually, in 16 May of 1960, so 63 years ago, Mayman invented the first solid laser, so the ruby laser that and it is famous his statement, a solution looking for a problem. So our work is based on the use of lasers, and we use laser for different applications. So laser ablation liquid, laser-induced breakdown spectroscopy, pulse laser deposition, and laser-induced periodic surface structures.
Antonio, please, your slides are not moving. You are still in the first one, and you are not in a presentation mode.
Okay, I'm really in the. Can you see it?
We see the slide, but we see the first one. You got to go on in the presentation mode from the PowerPoint. Okay, now you have the second, but it's still not in the presentation mode.
I'm in the presentation mode, but I will find a way. Let's.
Probably you are sharing another monitor if you have to monitor.
Okay. I'll try in this other way. Let's have a look if it works. Okay. Can you see it?
Now it's okay.
Now it's okay. Does it work? Okay. So as I said, in the south of Italy, we have snow sometime, and we find the solution so you can get released because of mean that can remove the snow, of course. But as I said, we work with lasers, so our problem is the other way around. So we look for problems rather than solution, because the laser for us is the solution, as said Mayman in 1960, so 3 years ago. Actually, the laser and the principle are based on the discovered by Taunis Basov Prokhorov that awarded the Nobel Prize in 1964. The systems that we use for our work, research work, are, of course, different way of using the light, amplified and by stimulated emission, so lasers, laser-induced breakdown spectroscopy, laser ablation liquid, or pulse laser deposition, and laser-induced periodic surface structures. So there is a movie showing our place where we are located. This is just a short movie or ablation liquid, so the cavitation bubble, how it evolves in time, and even the way of getting some treatments of diamonds in order to improve the absorption of this compound for solar devices, I mean, for concentrated solar devices. And so, as Mayman said, we look for problems. So our main objective is to use the laser matter interaction in different processes, and for getting different pieces of information of the process induced by laser, and even for getting new materials or devices. The laser ablation process is based on the interaction of the laser with material and the formation of a plasma plume, which by using femtosecond sources actually is formed by two components. One, ionic atomic species, which are much faster than the second part, which is made of nanoparticles. All emission of the plasma induced by laser can be even used for analytical detection of the excited species. And so we use this kind of feature for laser-induced breakdown spectroscopy, so for characterizing materials. Looking at the interaction of short laser pulses with matter, we get nanoparticles, as I said, and it can actually represent roughly 80% of the matter removed from the sample. And one of the mechanisms that can let us understand which is the process induced is the photomechanical effect. So we have a large amount of material that is ejected in form of nanoparticles. And the emission that we can get is from the ionic or neutral species, electronically excited, but even for longer times by hot nanoparticles, which can give a black body emission, which gives us the value of the temperature involved, which is roughly in this case, 3000 Kelvin. So it means that we can have a different evaporation of species involved, and at high temperatures, we can have a sort of fractionation of the composition. But actually, the radiative cooling, radiative vaporization cooling can be so combined that the deposited nanoparticles do not change actually for very high temperature, even though the difference in terms of vapor tension is of 1 to order of magnitude. So we can retain the composition of the starting target, even though we get nanoparticles, which are hot nanoparticles that are deposited and that can evaporate differentially in some cases, but actually doesn't happen for high temperatures involved. The difference between femtosecond and nanosecond is that we can retain the properties of the starting target, and in these circumstances, we can have materials for different applications, for biomaterial, refractory material, battery material components. In laser ablation liquid, there is another effect, which is the evolution of the plasma, but as well, all process involves first a shock wave and then a cavitation bubble, which is 1 or 2 order of magnitude slower than the shock wave evolution. And actually, we have a oscillation of the bubble, and you can see the move here, where the nanoparticles are formed. But when these are generated, when the cavitation bubble collapse actually, and some high temperatures and pressures are obtained, are reached. So in terms of pressures, we can reach giga Pascal and temperature of 10,000 Kelvin. So we have high temperature, high pressures the cavitation bubble collapses, and we have generation of nanoparticles, which can be strongly affected by the surrounding liquid composition. So this is just a sketch of what is going on in time, and the shock wave that evolves with a speed of actually 1 kilometer per second. What we do for characterizing our materials is to have a look at species by TEM, SEM, IFM, and all material science characterization that can help us in understanding what is the process involved, even the properties of our systems, and for application for different devices. In this case, we have obtained in liquid the ablation of titanium, which after a few days from nanoparticles, we have the formation of microtubes by self-assembly of them. And actually, the mechanism is induced by the presence of titanium hydroxide. And as well, because of the high temperatures and high pressures involved in the process, we can even perform the colloidal formation of our nanodiamonds. About the laser-induced periodic surface structures, we obtain by femtosecond laser applied, so in impinging on surface of materials, different nanostructures which are formed by ripples, and by Fourier fast transform, we can get the spatial periodicity of our nanostructures. And in terms of properties, even the composition can help us for different application. In this case, we have seen that simulated body fluid can grow some calcium phosphate species because of the composition and periodicity of our nanostructures. The lips can be split into different regimes. Low spatial frequency lips, when the spatial frequency of our nanostructure is roughly comparable to the wavelengths of our laser, or high spatial frequency lips, when the spatial frequency of our ripples is much less than half of the wavelengths of the laser. In terms of application, we have seen that these nanostructures, these ripples, can be very useful for increasing the absorbance of some materials like diamonds, as we saw in the previous movie. We can get the nanostructures in vacuum, but even in by using a workstation, which actually provide the nanostructure by focusing the laser beam onto the sample in air, in atmospheric environment. And in this case, we have seen that the molybdenum nanostructures induced by femtosecond laser can actually vary the optical properties by enhancing the selectivity in absorbance of the light. And a part of the nanostructures, we can have even nanoparticles that can be deposited on the nanostructure. We can even improve the absorbance of the solar light, but actually, if we use these devices in working condition, let's say 1100 Kelvin for a long time in vacuum, 10 to the power minus 5 millibar, we can see that the composition still remains the same if we use low fluencies. So it means energy per square centimeter, but actually we decrease the absorption solar light, and when we increase the fluence, we retain the solar absorbance because of the presence of sub oxide species like molybdenum for oxygen 11. And that can open new perspectives for improving the nanostructures in terms not just of the frequency of our reports, but even the composition. Some other application recently we have seen that by nanostructuring stainless steel, we can improve the anode-less lithium metal batteries performance up to 100% for a high number of working cycles. We have developed even a new way for adjusting the features of our surface treated by laser by applying two different pulses delayed one each other. And in this case, we have used the dual pulse lips by using a Michelson-like interferometer. So by changing the delay line, so the delay between one pulse and the other, we can actually change the structure, nanostructure, surface nanostructure of our samples. In this case, we see that we can have a structured surface with very short delays, and we miss that dimensional nanostructure by longer delays. It means that it's different way, of course, of the interaction between the first and the second laser beam because of the excitation that are induced by the first and interacting with the second laser incoming beam. So, for example, in diamond, we can improve the optical properties, the absorbance properties, just by varying the delays between the two laser pulses and reach even very short spatial periods, which are roughly in the range of 100 nanometers up to 80 nanometers. And recently we have applied this to other systems. So, and the last one, but we are still investigating this, let's say, high order and symmetrical appearance, like the hexagonal aspect that you can see in this picture. In conclusion, we get back to the Maiman statement. Laser is still a solution looking for a problem even after 63 years. And I would like to acknowledge all of you for your attending this talk. Of course, all team, working team, for its support, which is, at the Institute of Structural Matter of Tito, Monte Libretti, but even at University of Basilicata and University La Sapienza, Rome. Thank you for your attention again.
Okay.